Okay, so number 34 to 38 is a cluster question, and we have some information here. And what we want to do is kind of scan it a little bit and get to the question. Looks like we have a formation reaction. We have elements, okay, or atoms or chemicals in their elemental states forming a compound. This is really a heat of formation. And notice this is per 1 mole of KCl. And notice they're putting reaction here. And that's important because you can see that that's the energy change per any one of these values. Normally in a heat of formation we'd say mole of the actual product, but here they're saying reaction. Okay, so there we also have some information here regarding different types of letters that we're going to use to somehow relate to this overall reaction. So let's get started and be crazy and start with 34. How much heat is released or absorbed when 0.05 moles of chlorine gas is formed from KCl? And that's really the key word here, formed. Okay, so for formed from KCl, that must mean that we are headed in the reverse direction. So we're forming chlorine. Okay, and of course, when we're dealing with delta H's, it's always per how much. So that's 0.05 mole. Okay, so the bottom line here is in the forward reaction, we see there's a negative value for the delta H of the forward reaction. And if we're going to go in reverse, the delta H of the reverse is going to have to be a positive value. Therefore, I know it's endothermic, and therefore I also know that energy is going to be consumed or absorbed. So A and B get thrown out because we're dealing with the reaction of KCl, okay, going in reverse to form chlorine gas. Okay, and I'm writing the same coefficient, so that's important to realize we're going in the reverse. Certainly I could write it KCl, okay, this way if it makes you feel better, okay, but it does not matter here. Okay, back to the potassium. So the question is the value. So we're going to have to do our math without a calculator again, but we can handle this. What do we know? Well, we know that delta H is 437 positive value. Okay, I'm not sure why I wrote a K there, but 437. Okay, 437 kilojoules per reaction. Now let's go back into the reaction. Okay, and what do we see? Well, we see that we have half a mole of chlorine. Okay, now you may say, well, do I have to have that? Well, the thing is, this is the energy, and again we're going in reverse, so this is the energy here that it would take for half a mole of chlorine. You say, well, wait a minute. Okay, how do I know that? Well, because they said reaction here, that was the key. This is the energy change per reaction. So if we're going to go look at the forward reaction to understand this, notice there's a coefficient of 1 here. So if I have 1 mole of potassium being completely consumed in this reaction, this is the energy that's released. And if I have half a mole of chlorine gas being consumed, it's the same energy. Okay, so very important you understand as this energy is being written out here, it's either for any one of these chemicals. Notice the arrows I wrote above here. Okay, so that means that this amount of energy is released when we use up half a mole of chlorine, and it's also the positive value of energy as we do what? As we produce a half a mole of chlorine. Alright, so this is the energy per what? Really 0.5 mole of chlorine. Alright, now they don't want 0.5, they want 0.05. And you can see that, oh my gosh, I don't have a decimal place, but 0.05 as compared to 0.5, which is 1/2, is only one more decimal place. So I'm going to divide essentially 437, okay, not by 1/2, okay, but by 0.05. Now, per mole. Now, the key here is it's 437 per 1/2 already. See, that 1/2 is telling you this is the energy per 1/2 already. Okay, if we wanted per mole, we'd have to double it. But guess what? They want it per 0.05 mole, which essentially is 1/10, okay, of this. So all I have to do to this number, okay, is make it 1/10 smaller. So if we think of it this way, 437 kilojoules per 0.5 moles. Okay, and if you think about it, that's the energy per 0.5 moles of Cl2 formed. But what if we have not 0.5 moles, we have 0.05. See, 0.05 is really a tenth of this. This ratio doesn't change. This is the energy per 0.05. This is what it's telling us. So basically this per reaction and having this half here tells us. Okay, yes, we're going in reverse. But so that ratio, 437.5 moles, is fixed. Okay, that's not going to change. Now, if I have only 0.05, now how does 0.05 relate to 0.5? Isn't 0.05 a tenth? Are we moving our decimal place, okay, one place over? And then we're getting, okay, a smaller number. This is a what? This is 1/10 of 0.5. Okay, so if I know it's 437 per 0.5, and I only have a what? A tenth of that value, then I only have a tenth of 437. And what's a tenth of 437? Okay, and of course that would be 443.7, and that is the answer. And it's positive because we're going in reverse, and the reverse is going to be a positive value. Now, if you don't like the way I thought that through and want to do it a little bit more mathematical, what I could do is take 0.05, and that's the moles that we want. We can times it by the ratio. And what's the ratio? There's 437 kilojoules of heat absorbed or consumed, I like that better, per 0.5 moles. And you could times this to your heart's content and use a calculator to get the same answer. Okay, however, okay, you may not be able to do this in your head or longhand, but I do mathematically. Well, what is this? Isn't this the same thing as saying 0.05 mole over, okay, this guy right here, 0.5, and then we'll times it by 437 kilojoules. Okay, well, you can probably do this in your head, right? Okay, so this is mole over mole, so that would cancel, right? But the point is, 0.05 is a tenth of 0.5. And then you take that 0.10th, okay, this is equal to 0.1, right? And then you're going to times it by this number. And that makes this decimal go smaller by a point, and that's why it's 437 kilojoules. All right, so that's why number 34 is C. On to 35. Okay, number 35, what remains in the reaction vessel after equal, that's important here, equal masses of potassium and chlorine have reached, okay, until either one or both of the reactants have been completely consumed. So this is a limiting reagent problem. They're going to have equal masses, okay, equal masses of both reactants. We know that the coefficients written in the overall reaction are not a ratio of how heavy, but a ratio of how many. They're moles, not masses. So given that play on mass versus moles, what can we do to see who is the limiting reagent and who is the excess chemical? Because what they're asking you is which remains, what remains in the reaction vessel. And what remains in the reaction vessel is going to be the product, okay, of the reaction, which we know is KCl, and also the excess chemical, the one that is in greater quantity, okay, that doesn't run out first. Those are the two things. So it's not going to be all three. So D is crossed off. The question is, it's not going to be just KCl only. Someone's going to be limiting. So the question is B or C. All right, now, what will be helpful is for us to write the chemical reaction. Since I have it above here, it's just a little redundant. Don't have to go back and forth. And what we have, so if we take potassium, and notice there's no number in front, so that's 1. Then we have the 1/2 chlorine gas, and of course that makes the KCl. And I'm writing this to set up our limiting reagent problem. I know we don't have calculators, but we can do this. Now, the first thing we have to realize is we're going to have to assume some value. Before I have an ice table here, and this is a stoich table. Remember, this is a stoich table that we would have to have molarities. Now they didn't give us moles. They said not equal molar, they said equal masses. Okay. Now equal masses, what masses could we possibly use? And I know that people can see this right away if it's a 1, okay, to 1/2 ratio. So 1 to 0.5 ratio, some people can see right away that if we have equal masses, okay, possibly. But the best way to do this is to use a mass that's related. Of course, it's going to have to be related to its molecular mass. So let's go to the periodic table to look up the mass of potassium and chlorine, because that's really the key here. You can't really see it right away unless I was giving you a mole value. So I'm sorry, you really need to go see what the atomic masses of potassium are and the atomic masses of chlorine are. That's the key in this problem. So let's go to the periodic table. Over here we have our potassium. Okay, atomic number 19. This is the mass number below it. It's got that decimal point because we should recognize that the atomic masses of elements is the average of all of the existing isotopes rounded to their percentage abundance in nature. And chlorine's atomic mass is 35.45. And that's really, really important to know their atomic masses. All right, so why is that important in this problem? Well, let's pick. All right, let's pick a mass. And now you don't have to pick the atomic mass, but I'm going to do so to make life easier. Remember, we have potassium and we have 1/2 chlorine gas here, okay, becoming KCl. All right, so let's pick a mass, and that mass we're going to pick is 39. Let's just round this off to 39. Let's pretend that's 1 mole. Okay, so if I have 39 grams of potassium, okay, that's approximately 1 mole. And I know that it really should be 39.1, but okay, let's make it 39.1. Bottom line is, in my Stoich table, I have 1 mole. Now, for all of my potassium to disappear, what do I need? Okay, as we've done so before, I need what? 1/2 of this number to make all of this, to make all of potassium disappear. So I need 1/2 a mole for all of, at least, okay, to make all of this disappear. All right, now, if we're going to choose 39 grams, the problem said equal masses. That means I have 39 grams of chlorine, okay, and that's, of course, Cl2, right? So, if chlorine is 35.45, and we can just round that to 35.5, Cl2's molar mass is going to be 70, or 71, I should say, grams per mole. Okay, so if 1/2 a mole is what's here, so what's 1/2 of 71? 35.5. So essentially, I have 35.5 grams, I should say, is needed. That's needed because that's going to equal what? That's going to equal 1 mole. I'm sorry, that's going to equal 1/2 a mole. Okay, right? Because 71 grams, that's 2 times that, 2 times this value here, is going to give me the Cl2 value. But because of this half here in the equation, I need 1/2 a mole. So 35.5 grams is needed. But what did we choose? We chose 39 grams. So what we have is 39 grams. Okay, so what we have is, we have something that is greater than 0.5 mole, right? 1/2 a mole would be 35.5. That's what this is, right? I know it's 1 chlorine, but the molecule is Cl2, so the actual value is 71 if you round to 35.5. And since the stoichiometry is a 1 to 0.5, in order for all of the potassium to disappear, I need at least 0.5 moles, which was equal to 35.45 if you want to keep it there, or 45.5. But because we said we had equal masses, and we're choosing 39, okay, clearly 39 is what? Greater than the 35.5 value, which is the 0.5 mole. So we have what? more than 1 mole. So if we get rid of all of this, and some people see it right away once you see the moles, but if you get rid of all of this, okay, and we put something like 0.6 moles, and I don't know what that number is, and I don't care. Remember, this is 0, and we can complete this Stoich table, okay, by doing the following. This is the initial. This, because of equal masses, we have something greater than 0.5. That's how we figured this. I'm making up 0.6, but it's greater than 0.5, and it'll work for this problem. 2, what's going to happen is we're going to be minus 1 mole. Now why? Because we just said this is a 1 to 1/2 ratio, right? So in order for all of this mole to disappear, I need to have 0.5 moles of this. I have more than enough. So therefore, this is going to be minus 0.5 moles. And because this KCl has a 1 mole ratio, it's going to be plus 1 mole as well. And at 3, this is going to be, I should say 3. I really should keep this, well, this is initial. Sorry, why I was counting is beyond me. Okay, so everything's moving. Sorry. So we have initial, we have the change, which is minus. Remember, this is the limiting reagent, right? Because we have just as much as we need. We have enough. We need half of 1.5 mole. We have more than enough chlorine to make all the potassium disappear. So this is the change. And this is going to be minus 0.5 because we're going to use up exactly 0.5. That's exactly what was needed to make all of this disappear. Hey, it's a 1 to 1/2. And this is a plus 1 mole because why? Because it's a 1 to 1. All of the potassium that we're losing becomes the KCl here. And at the end of this driven completion reaction, okay, we're going to have 0 limiting reagent left, and we're going to have 0.1. And again, I made the number of 0.6, but there's going to be something there. And then, of course, 1 mole. So if you think about it, what's going to remain in this completion reaction? The things that are going to remain are going to be the chlorine gas. We're going to have some at the end, and we're going to have some what? Some of the product. So it's going to be KCl, the product, and the chlorine, the excess chemical that we determined, okay, because K was the limiting reagent. So back to our choices. Equal masses of K and Cl until one of the reactants have been completely consumed. That means goes to completion. We would make our product. And we just found out that chlorine would be our excess chemical based on its what? Atomic masses. So C is the answer for number 35. On to 36. Okay, number 36. Which of the values for the delta H for a process in the table is less than 0? They're very nice to you to help you understand that being less than 0 means that it's an exothermic process. We all should recognize that exothermic means that we have a reactants becoming products and that we have energy or heat being released as one of the products. And we're looking at a potential energy diagram that's going to start with very high and go low. Here's the pathway of the process, and our delta H is the difference of where we start and where we finish. So this value here is delta H, and of course it's going to be negative because we're going down. And if this is potential energies, the energy in the bonds, you can see that the reactants have a tremendously high amount of potential energy and the products don't. How did the products have less energy? That energy had to be released. Okay, so that's really, really important to understand. So we're going from a system that is unstable with high energy, so this is unstable, to a system that is stable. And how do I know it's stable? Over here, because it's low energy. We're moving from a system that has a lot of stored energy inside to a system that has a little bit. Remember, this value here is the amount of potential energy in the reactants. This value here is the amount of potential energy of the products. Why the products have so low? Because some of that energy, okay, that the reactants had was given off as the heat that we just talked about. And all exothermic reactions move this way. So we're moving from an unstable high energy reactant to something that is lower energy, and that'll help us figure out which of the individual components of the table is releasing energy. Let's go to the table. So let's go through this. We have a solid potassium going to a gas. And we should know that a gas has tremendous potential energy because these molecules are flying around hundreds of miles an hour, and a solid is limited to wiggling in its fixed position. So we're going from, in this case, very stable to unstable. And that would mean we're going from what? We're going from a position of low energy to a position of high energy. And that means at delta H, okay, the change in enthalpy would be positive. You need energy to vaporize something. Solids that become gases, this is sublimation, require energy because gases have more energy than the solid phase. So this would not be a good choice. We would not be picking V. Okay, we have a gas going into a gas, but more specifically, easy for me to say, we have an atom becoming an ion, and it's shooting out an electron. My friends, this is ionization energy, and you should be able to identify ionization energy because we use it a lot to figure out the valence electrons from the one that's a huge leap. So this is ionization energy, and it's the energy needed to pull an electron away from an atom to make a positive ion that we call a cation. These values are always positive because electrons are going to be attracted to the protons in the atom. Now, how much energy it takes to pull these away will vary based upon how tightly held they are. You notice the metals do not tightly hold them. That's a major property of nonmetals do. But they're always going to be, okay, an atom is always going to have low energy, and of course, to pull an electron away, it's always going to need energy to get away from the electrostatic attraction. So this is not about getting stable as an ion. I know potassium becomes an electron configuration. It's more stable than K, but we're talking about the energy needed to pull this electron away. And this is an electrostatic force. And because it's attracted to the positive protons, we're going to need energy. And all ionization energies are positive values. So this is definitely a choice. Okay, so and that one might have got you a little bit, but all ionization energies are positive values because all electrons in atoms are attracted to their nuclei or the protons in the nuclei. Again, they may be higher or lower values, but you always need energy to pull electrons away. Obviously, if you're pulling electrons that are core electrons, tremendously higher than the valence electrons, but still you need to add energy, and that's why you would have a positive change in enthalpy here. So this is definite choice here. Okay. All right. Now have a look at this one. Chlorine gas to chlorine gas. Well, that's not a change of phase. Look carefully. It's chlorine Cl2 becoming two chlorine atoms. What's happening here is we're breaking the bond between the chlorine. Okay. So the chlorine molecule has a bond. And what we're down to do is, if we talked about it, bond energies, or better yet, bond enthalpies, right, are always going to be positive values. So why? Because bonding creates a stable state for atoms. They're using each other's electrons to achieve a lower energy configuration for both. So bond energies are always positive. If you remember our potential energy diagram, if we have something that's endothermic, like this, it takes energy to what? Break the bonds. And energy is what? It takes energy to break the what? The bonds and the products. What we do is to find the total enthalpy. Here's the energy it takes to break the bonds, and here's the energy it would take to reform them. So always are breaking bonds, it takes energy. So bond enthalpies are always measured as positive values. But when we figure out delta H, we understand the energy it takes to break the bonds into what I call the Faz zone, the free atom zone, okay, is the same energy released when you form them. All right, but the bottom line is bond enthalpies are always positive. It always takes energy to be absorbed, okay, or consumed to break a stable state. Remember, I call the free atom zone up here. And for these compounds that have this energy, it takes this amount of energy, or I would say higher now, right, to get to that free atom zone. And it takes even this. And so that's a measure. Let's do the green hours. This is a measure, the green hours, of the bond enthalpies. It takes energy to get to a higher unstable zone here, the free atoms. So this is a good choice as well. Moving on to the fourth row here, chlorine plus an electron. Okay, this electron affinity. And we have to realize that the non-metals that are up to the right in the periodic table, they absorb and take on electrons very readily. Okay, and so this makes this chlorine atom very stable. And so this would be an exothermic reaction. Delta H would be released in this example. Okay, so this would be negative, so we would not consider this. Okay, so to add an electron to elements that love to grab electrons, generally speaking, the upper right hand corner, the electron affinities, okay, chlorine has a great affinity for an extra electron, as do most of the halogens, because they're one away from becoming like a normal gas in the electron configuration. What we found is that this one would be a negative value, and that is one of the ones we're going to consider because delta H is negative. These ones, the first, the second, and the third row, all are positive delta H's, meaning they require energy. So we wouldn't consider 1, 2, or 3. Sorry for some of these checks here. I'm just checking that there. So this one would be negative for reasons we just explained. And the last one, we have ions in a gas phase becoming a solid, and this is essentially a measure in part of lattice energy, the energy it takes for to see the stability of a crystal lattice. But in this case, it's looking just at the ions, okay, coming together into a solid. Now KCl is still ionic. If we were to draw the ions, we'd have positive and negative ions in this crystal lattice, okay, and that we could go in all directions, and this is the ionic bonds in this one-to-one formula of this crystal, of this salt. And whether they are in a solid phase or a gas phase, they're still ions. So really, essentially, this is a phase change here where we have gases becoming a solid, and for gases who have tremendous energy to become a lower energy solid, energy has to be released. So this delta H equals negative. So the only choices that provide an enthalpy, a delta H, it's less than 0, that release energy, okay, are the Y and the Z only. Let's go back to our choices. So choice B is our answer, Y and Z only. The only two choices that create a scenario where we're going from unstable to stable. And why, again? Very simply, okay, if you look up, okay, we're going from a chlorine atom that is just more stable as a Cl negative. And so the forcing an electron, the electron affinity will be delta H is negative here. That one you may not get, but that's the reason here. And this gas ion becoming solid ions have to go down in energy if you're going into a solid. Don't get fooled that KCl is really different than the K plus and Cl. It's just the what in that areas, and the rest of these are going the opposite way. These guys are going to less stable conditions, okay, from a solid to a gas, and then of course in this case needing energy to pull electron away. Okay, this is a tricky one, the second one, and of course the energy needed to break a bond. And for 3, I understand why people would pick W. That is a slippery slope there, because you may say, well, K plus is more stable than K, and that's true, but there's overall energy needed to pull that electron away that felt that proton. Okay, so the best answer is going to have to be just Y and Z. Okay, why? Because it's Z2. All right, so 36 is B. On to 37. Number 37, it is observed that the reaction producing KCl from its elements essentially goes to completion. All right. Which of the following is true statement about the thermodynamic favorability of the reaction? All right, so we're talking about pathway. We're talking about why it goes to completion. If something's going to completion, that means the reaction is going forward until it stops. There is no what? Equilibrium. So if we look at the reaction, let's look at the reaction above, and there are some hints here. What are they talking about when they talk about thermodynamic favorability? They're talking about the pathway. And what about the pathway? Well, if it goes to completion, we're talking about this going forward, and that's why there's no double arrow here. And we're talking about the fact what's creating a pathway for this to go in this direction? Well, we should know that the delta S of the universe, okay, is increasing. We're going from a what? Essentially, entire universe in this reaction, we're going from a concentrated source of energy to a less concentrated source. Okay, but there's two factors, and what are they? Well, we measure the delta S of the universe by looking at the what? Systems values of heat flow and the systems value of particle degrees of freedom. And we use delta G is equal to delta H minus, and I put H, but I wrote T, delta H minus T delta S. Okay, so what we look at is that they're giving us the delta H is negative. So this is a negative value. Okay, this is a minus sign in the equation, and then we're going to have this parentheses. Temperature is Kelvin, so it's always going to be positive. So it's about the delta S. Let's look at the particle freedom here. We have a solid, and we have a chlorine gas molecule. So we've got one, and then we've got another gas that's kind of bonded to itself. So we've got two particles, okay, and they become this solid that's in a crystal that repeats over and over and over again. So we really can't look at the number of particles, but we can say the freedom definitely decreased, because although we had one solid, we definitely had one what? Gas. And so essentially, we've got part of this gas being locked into a solid. Okay, notice this solid was by itself. It's still going to be in a solid phase, but we're going to put a gas into this crystal. So if you think with me, if one of these guys are flying around, okay, hundreds of miles an hour, now they're going to be locked and just vibrating slightly in a solid, you can see that the overall delta S of the system has to be decreasing. We say negative. Important to know your signs. Delta S is the measure, okay, of particle freedom, dispersion of energy. We're going to take this energy of a gas that's flying around, and we're going to lock it into this solid. You're losing degrees of freedom here by taking a gas out of the surroundings. So the delta S, the system, is decreasing. So I'm going to put that here. Okay, now we're going to do our math. So minus becomes plus plus. Okay, now for delta G to be negative, which means that there's going to be a spontaneous forward direction in that pathway, what do we have to have? We have to have a great enough negative for the enthalpy, delta H, to overcome this bad positive here. All right, so the only way we can have a completion reaction that goes forward, delta G has to be very negative. It must mean that this delta H is overcoming the bad delta S. So we would call this, even though they're not bringing this up in the equation, an enthalpy-driven reaction. That's what this problem is about. So when you go look at the choices, okay, it's observed the reaction producing KCl from its elements goes essentially to completion, which means it is spontaneous in the forward reaction. That means delta G is very, very negative. In order for it to be negative, okay, we have to say that the reaction is favorable. Yes, because it does work. Okay, so A and C are the only choices that make sense. B, unfavorable, makes no sense. Unfavorable, heck, they said it went to completion. By saying it goes to completion means there was a pathway that was favorable. But what's making go forward, it's because of the enthalpy change. So the reaction is favorable, driven by enthalpy. The enthalpy is negative enough, exothermic enough to overcome the entropy. This is an enthalpy-driven reaction, and this is an enthalpy-driven choice. So 37 is A. D, okay, would mean that both enthalpy and entropy changes, and it's when you have a driven reaction, I call that the sometimes rule. Okay, one is good and one is bad. All right, it's one or the other. If it was both due to both of these, then both of these would be favorable. They'd be negative here. Remember, it's minus T delta S up here, right? and this would be a what? A positive entropy if the particle freedom was going, and this would be plus a what? Negative, and now you'd have always a negative. It's the always rule that I call. So when delta H is negative, which is exothermic, and delta S of my system, okay, which is entropy, is positive, okay, these would both contribute by using your signs to a negative delta G, and I call that always rule. This was a sometimes rule because I had one favorable condition, an exothermic, and an unfavorable, a negative delta S, and the favorable was big enough to drive it forward. So 37 is A. On to 38. Number 38, which of the following expressions is equivalent to the delta H for the reaction represented above? Okay, so this is our reaction here, and each individual reaction has its delta H, and we know from Hess's law we can combine the reactions that make this to get the overall reaction. So we want to know what components of the table above, since we're using the letters that represent individual reactions, would make this overall. So let's write the overall. Cl2 plus 2 electrons give me 2 chlorine negatives. Remember, the enthalpies are additive from the individual steps that make this. Okay, so what we need to do is go find those steps. Okay, let's go up to the table and see where we can grab those electrons. Well, okay, well, it looks to me that these are the two that we're going to use, right? X and Y. X and Y is involved here because I want to have the chlorine going to 2Cl and then the chlorine plus an electron. So let's kind of rewrite those. Okay, see if we can do that and keep that there. So we've got Cl2, 2 chlorines. So we've got Cl2 going to 2 chlorines. And then we have the Cl, okay, gas, plus an electron going to what? A chlorine, negative. Okay, so this is X and Y. Let's put that in there. This is X and Y. Okay, let's scroll down. All right, so what we have here, we want to have two. Let's see what we can figure out to manipulate these equations. We know that we have 2 Cl negative here. So I'm going to times everything by 2 to get 2 chlorines in the bottom. So this becomes 2 electrons, 2 Cls. And I notice something. There's 2 chlorines here, so this is good. There's 2 electrons in the second one. That's here. That's good. And there's a Cl2 here. Hopefully everything cancels. And look at this. 2 Cl and 2 Cl cancels. So what did I have to do to make this equal to this reaction here? I had to take X, and I'm going to add it because I'm talking about enthalpies. I know that the enthalpies are additive for each reaction, even though they weren't listed. And what we do to the Y? Well, we times it by 2. That's what we did for this to be the overall reaction. And why did I times by 2? Because I noticed I needed the second one to have 2 electrons and 2 Cl negatives. And by timesing by 2, what I did is I created a scenario where I could cancel out this intermediate. Ooh, if this is a mechanism, right? All right, any case. So in any case, it's X plus 2Y, and that's how I did it. Okay, looked kind of a weird question, but actually when you think about it, all you're doing is finding 2 reactions that cancel out to make the overall. Okay, and it's a skill you have to have, and an easy one. So 38 is C. On to 39. Number 39, what we have here is a cotton ball with aqueous HX. It could be HCl or HBr. And a cotton ball with a volatile base. Okay, it's a base that produces vapors. Okay, and the bottom line is the vapors from one chemical will meet the vapors from the other chemical, and depending upon how fast these vapors move depends upon where the what? acid-base reaction occurs. We did this type of Graham's law of diffusion type of experiment we looked at, okay? When I had hydrochloric acid and ammonia, we saw where the ammonia, okay, if you remember in those little Erlenmeyer flasks, you saw where that white smoke existed. Here was HCl, here was ammonia, and if we look at the atomic mass, because we should know that the speed of these molecules is related inversely with its mass. Remember, kinetic energy is equal to 1/2 the mass and the velocity squared. So they're both the same kinetic energy, which is temperature. Okay, if I have two different compounds, as we've talked about, all right, if they both have the same kinetic energy, if one has a greater mass, they have to have lower velocity, which is less speed. Makes sense. Bigger molecules move slower. And if I've got a lower mass for the same kinetic energy, I have to have a greater velocity. Now, we derived Graham's law of diffusion, which is basically says that the rate of escaping and opening or mixing out the air is inversely related to the square root of the molecular mass, but don't worry about that. All you need to know is that bigger molecules that are heavier move slower, and smaller molecules that are lighter move faster, okay, at the same temperature. And that's pretty intuitive. So they're saying in this question, which of the following combinations will produce a solid closest to the center of the tube? So if they're going to have a solid to the center of the tube that I just draw here, meaning they're going to create a salt, usually acids and bases make a salt, right? And water, if this is going to be toward the center, that means that these have the what? Similar or the same speed. And if they have the same speed, they must have the same mass. So really, with your periodic table, figure out which ones have this similar mass. Now, for me, I eyeball this, I see HBr. And I know if the halogens are fluorine, chlorine, and bromine. And so if you think with me, this is, and helium, of course, is up here. This is N equals 4. And I know as we go down the periodic table, all right, the mass of the elements get bigger. So I know that I'm going to get rid of this because I'm not going to look that up. So now it's between HCl and these guys who have the similar atomic masses. Now, if you don't know your atomic masses, go look at the periodic table. You're looking at the value that has the decimal place because, again, that's the average isotopic mass of all the known existing isotopes with their relative abundances. So if I'm not sure if it's A or B, I do hydrogen has atomic mass of approximately 1. I'm going to round here. Chlorine we'll do 34. And then we have nitrogen, which we should know is about 14. And then we know we have hydrogen, it's 1. Okay, so if I do hydrochloric acid, 1 plus 34 this is about 35. And then ammonia is, what, 14 plus 3, 17. So there's a big difference here, and this is the demo I was just talking about here, where when I opened up these stoppers, immediately you saw, okay, the smoke, where would it come from? Well, the lighter gas, ammonia, is going to actually meet the hydrochloric before the hydrochloric can actually leave. You'll see the smoke going into and leaving here immediately, okay? But in this case, we wanted when they're about the same. So again, we have 35. We just did that math. And let's go figure this guy out. Carbon, we should know, again, if you have to look, it's a 12. It's the mass of 12. I know it's 12.00 something, but we're going to use the rounded. And so we have 12, and then we just found that the H is 1 apiece, right? So that's 5. And then we have nitrogen, which is 14. And you do the math, and you get 6, 4, 2, 6, 11, and you get 31. Okay, so the atomic mass of this organic molecule is 31. And this one's 35, and that's a heck of a lot more similar than 35 and 17, and these numbers will be even bigger because bromide being in N equals 4 energy level is going to have a much, much larger atomic mass, and that will skew your results there. So the best answer, the one with the most similar, and if you had to go through C and D and do the atomic masses and find out which was the same, hey, so be it, get it right. But A is the choice where the two molecules have the most similar atomic masses, therefore the most similar speeds. sides. Therefore, they're going to equal the same amount of ground and meet more in the middle. So 39 is A on 240. Okay, so number 40, silicon crystals are semiconductors, and we should know that because they're metalloids or semimetals. They have properties of both metals and nonmetals, which means if you're in my class, we learned about gap theory. The gaps aren't so close that electrons can equally conduct, but the gaps aren't so far either. They're somewhere in between. So they're not great conductors, but not bad, if you want to talk about it that way. Which of the following is the correct reason for increases in the conductivity of silicon crystals when a small fraction of silicon atoms are replaced by a different element? Okay, and we call this replacement of silicon crystals in transistors doping. Okay, we basically add elements, doping, I-N-G, we basically add it to increase performance, okay, to help with this. Now, a semiconductor in a transistor essentially is a we'll do NPN kind of a conductor here. And this is what we have. And so we have these are in here in this transistor. And a transistor, we're going to learn very simply, is this basically an electronic switch that can be on or off. And all of our memory in computing power in machine language is either an on or an off, one symbol or a zero. And so we use transistors for that language or for the memory. It's kind of interesting how we can use a crystal that basically is an on and off switch that has no moving parts. Now in this crystal here we have silicon, and if you know silicon, it's underneath carbon. And if you know carbon, carbon has 4 valence electrons. Carbon, okay, we have nitrogen, we have oxygen, and we have fluorine, and then eventually we have our noble gas, neon. All right, now, when we look at here is that we know that this has its filled octet. This is 1 away, this is 2 away, 3 away, and so we know this is 1 valence electron, or we would say that, I'm sorry, it becomes -1. So this is row 18, row 17, row 16, row 15. And you don't have to know this by heart because you can look at your reference table. And what I'm getting at here is that we have 7 valence electrons for the fluorine, 6 for the oxygen, 5 for the nitrogen, and 4 for the carbon. Carbon wants to fill its octet. All right, and we can do electron configurations to prove that. And we can say that the noble gases have their 8. Now, the point I'm trying to make here is that we have silicon under carbon. And we know that silicon and carbon, because they both have 4 valence electron, the silicon will make that tetrahedral shape that we talked about, all right, the same way that a carbon is made. So here is the tetrahedral. Here's one position, here's another position, and one coming at you. And this is an Si. And it will bond with more silicons in all direction. All right, now, because the gaps are small but not so big, they have some conductivity but not great. And so what we do in the crystal of silicon is we essentially add 2 different types of chemicals. Now, if you notice in this transistor, what we're going to do is we're going to have a source. Okay, this would be the source. This would be the drain. Okay, this is where we would have, you know, 1 electrode, and then we would have a gate. And this gate is where we would add another voltage right here. Okay, now don't worry about it. This is a source, and this is where a drain of electrical input, and this is another voltage being put in here. Okay, in this area right here, we have the silicon bonded to what? Silicon bonded to silicon, all in tetrahedral formats, right? Bonded to silicon, bonded to more silicon. And it basically is a network solid, as we've talked about. All right, now what we do in this crystal of silicon bonded to silicon, and I'm just going to draw it flat right now, okay, is we eventually on one side, on this side, the N-type, okay, for negative, we're going to put in a compound here that has more electrons than the 4. And so phosphorus is used on this side. Now you don't make all this silicon. Remember, silicon is here, but we change out some of the silicons, not all. We dope it by making some of these have phosphorus. Oops, I'm not sure what's happening there. But the reason that I do that is by putting some phosphorus there is I know that phosphorus okay, is next to silicon. It's under group 15, and it has what? One more valence electron. Yeah. And so it's going to bring another electron in the crystal. So if we have a P where a silicon should be, it's going to have an electron that's not really bonded, and therefore this electron can move throughout the crystal and give it some conductivity. That's how it helps. Now in the positive P part of the transistor, we add another compound, okay, in the silicon. We dope it a little bit and we add boron. Now if we check out boron, all right, don't be a boron, you're going to see that boron in essentially is row 3. It has three valence electrons. Okay, so when boron fits into the silicon crystal in this area, okay, let's get rid of the P and put a boron. Boron, and okay, can't bond to four things, and therefore has a hole. This silicon was here, and there should be a bond here, but it doesn't have an electron to do so. So there's an electron here for silicon, but boron doesn't have one. Okay, so we would call this a hole, and these holes are positive. And this is what electrons that are free in the what? In the n-type, the negative type that have the what? The phosphorus that brings one more valence electron, they are attracted to these holes. So what happens is these electrons diffuse to this area here. And when they do so, they make this area very negative. And that negative area, okay, prevents any more electrons from passing through. Okay, it's called depletion layer. When we put a positive volt here, little voltage, by making this area positive, it can attract electrons from the phosphorus in the doped silicon to overcome this negative, and now we have a switch that's on. It's off when we don't have a positive because the depletion layer builds it up, and it's on and off. So this is just a little bit of how a transistor works, but you could have worked this out by reading carefully which of the following is the correct reason for the increase in conductivity. What do we know about conductivity of crystals? Okay, for metals, they have to have free moving electrons. Well, by adding phosphorus, who additional mobile negative charges, because it has one more valence electron, it's going to increase the electrical conductivity, and that's why they call it the n-type area. This would be NPN type of transistor. So p atoms introduce an additional mobile negative charge. So that's why A is the best answer. P atoms introduce additional mobile positive charges. Now, that's what boron would do. Okay, germanium have more electrons than silicon atoms have. Now, that may be true, and we can check that out, but that's not what they're after. Let's go to the periodic table, look at germanium versus the silicon. So there is my germanium, okay, and there is my silicon. And you're talking about a transistor where we have an N, a P, and an N. This is the negative part of the transistor that's made of silicon crystals that have phosphorus doped with the silicon to add what? More electrons I talked about. And the p-type, in this area, we have the silicon doped with boron. And you say, well, why do we use boron? Because why don't I use something like germanium that has more electrons? Atomic number 32 compared to 14. It's, remember, the proton number equals the electron number. So germanium would even give more electrons. You may say that'd be more helpful, but remember your crystal understanding. Remember, silicon has a certain size to it. And to have these crystals of silicon, we better add atoms that also have the similar size. So boron and phosphorus, okay, can fit in the crystal very well. But remember, as we go down, remember this is n equals 1, 2, 3, 4, and n equals 4. Germanium is a bigger atom as you go down, and that bigger atom wouldn't fit very well in that crystal, and therefore germanium's not a good answer. We have to pick atoms that will fit in the crystal, and notice we picked phosphorus that has one more valence electron. Okay, and I'm sorry I named this 18, and this is 17, and this is 16, and this is 15, this is 14. They don't do that on your periodic table, but in most others they do. Sorry about that. But in any case, you should realize you're one away, one valence, two valence, three valence. You're 3 electrons away from being as stable as your noble gas, and carbon is 4 away. So we use boron, which has 3 valence electrons, because it's what? 1s2, 2s2, 2p1, or phosphorus, who its valence shell would be 3s2, 2p3. Okay, so it has 5 valence. So 5 valence electrons here versus the 3, the one with more valence electrons. That is what? About the same size that could fit in the crystal, would be more appropriate to add the negatives in the N area. Whereas boron, who is missing an electron, remember there's going to be a place where there is no bond that creates that positive hole where the what? The electrons from the phosphorus want to move to. Okay, so that's the reasoning why that choice isn't correct. Back to our choices. So as we just saw, that germanium, although has more electrons and would help in making that N part of the transistor to have those extra electrons by doping, would be very good, except that it's too big. Okay, so when we talked about alloys earlier in the year, we talked about interstitial and substitutional alloys. We need something to have the same, approximately the same size, and germanium wouldn't. And you may say, Mr. Grodsky, well, boron is not in the same energy level, so boron would be smaller. Yes, okay, but it'll fit a little better, okay, than the germanium, if you had to know. Germanium atoms are much smaller than silicon. No, they're bigger, so that's not even correct. This is correct that they have more electrons, but being too big would destabilize the crystal, so C isn't the best choice. So essentially we're looking for a choice that adds more electrons, one more valence electron, that it's about the same size of silicon. Now, believe it or not, transistors are part of the curriculum, and this is the only question I've ever seen it being asked. So again, not going to chase questions, but A is the answer for number 40. On to 41. Okay, number 41, N2 molecules absorb, take in, are able to take in wavelengths of ultraviolet light, but not visible light. Iodine molecules absorb both visible and ultraviolet light. Which of the following explains the observations? Well, one of the things that should jump at you is that if we're taking in wavelengths of light that are from the visible spectrum, so the Roy G. Biv, if we're taking photons of light that are part of the visible part of the spectrum, which is a small little sliver of the entire electromagnetic spectrum, we should realize that if they're absorbing part of that spectrum, and I'm going to draw a cuvette to help you remember this. When do we use cuvettes? They're from spectrophotometers, and we use them if in fact the chemicals have color. Okay, so why would a chemical have color? Well, it's because of its electron structure, because of how it's bonded, if it has those pi stacking, or hey, if it's a metal ion, in this case it's non-metal, so basically because of its electronic structure, does it have small enough gaps in energy levels in its molecular bonds that electrons can get excited, okay, and if they get excited and they can find their way back by another thermodynamic pathway down this lower energy level, they may have give off heat or so forth. If they're absorbing that small enough gap area to absorb a small energy photon that visible light is, whatever they take in is going to get transmitted outward. I'm sorry, whatever they take in, the missing light of the visible spectrum they're not taking in is going to be transmitted outward. Okay, some people like to say like green grass is green because it absorbs the red and the blue part of the spectrum and we see what's reflected. Okay, I like to say that the chlorophyll in the plants and photosynthesis, that it's green because it absorbs the other part of the visible spectrum and it transmits what it's not okay, being used. So colored solutions that we've tested based upon their color, how concentrated they are in our spectrophotometers, are colored because essentially parts of the visible spectrum are exciting electrons from one energy level to another, and they're using that specific energy that's measured by that what E equals Planck's constant times the frequency. It's of a photon. It's a specific energy photon that makes this electron jump to this energy level, and then again it finds a way to jump down maybe smaller increments, maybe by energy, by giving off heat, and eventually is back down again. But by taking that part of the spectrum and the spectrum that's not being used, you're going to see color. So this would jump out at you that there's something to do with having a colored solution. Okay, so look at A. More energy is required to make N2 molecules vibrate than required to make I2 molecules vibrate. Not sure here. The ultraviolet light is definitely going to make these molecules vibrate both, since they're both absorbing that. So I would say that that's not going to make a good example there. They're both absorbing ultraviolet, so I would say that they're both are going to make them vibrate. More energy is required to remove an electron from an iodine molecule than it's required to remove. That's not something that's also clear here. Okay, we do know that when you remove an electron, you're talking about something called ionization energy. And I'm going to tell you that normally visible light isn't great enough. Now, ultraviolet could be, but we don't have enough information to answer that there. Visible light does not produce transitions between electronic energy levels in N2, but does produce transitions in the I2. That is the best answer. Okay, when we have an electron transition from a low energy state to a higher, that means that electron is using part of the energy of that photon, and what it doesn't use would be what? Would be a color. So the idea here is that N2 molecules are colorless, whereas iodine molecules are not colorless. Iodine in solution, remember the starch iodine complex, which is that dark blue-black solution? Okay, they produce colored solutions. So therefore, iodine is able to absorb and have an electron transition to take part of the energy of that photon. Remember, visible light is all different types of photons of visible light. The iodine is going to basically take a segment or a fraction of that light, and what it doesn't use is what we see. So C is the best answer because iodine has a color. And we should know that from our biology and from the iodine complexes I showed you in the iodine clock reaction. Okay, so D, the molecular mass is greater. It has nothing to do with molecular mass. So the what they were after, okay, indirectly was noticing which one would have an absorption spectroscopy colored. Even though I didn't say it, it's about electronic transition. Okay. All right, so C is the best answer, 41. Number 42, to make gold, AU, stronger and harder, it's often alloyed with other metals such as copper and silver. Consider two alloys, and you should know what alloys are. Alloys are nothing more than a replacement of one atom in a metallic crystal with another atom. Okay, now sometimes those atoms are about the same size, and we call those substitutional because remember, crystal patterns, okay, are based upon size and distance. And so we talked about that in number 40 a little bit with the silicon crystal. But if we have the size of one atom is about the size of another, it'll fit right in there. The properties of this atom in this metallic crystal will give the other element that's in large quantity behave a little differently, give it some additional properties. Like for instance, gold is a very soft metal. It melts at a very relatively low melting point compared to others. So it's easily workable, but it's soft. To give it some properties to harden it, we do add other elements to it. Now, how do we make it harder? Well, again, this is a substitutional where they're about the same size. But we talked about carbon steel. Now let's pretend that this is iron. So these all are iron here. And then we're going to add carbon. Now, iron is a metal, and it's bigger. Nonmetals are smaller because their orbitals are pulled in because they have a great high Z number for their energy level. And so carbon is smaller. So carbon would fit like in the middle. It wouldn't fit in the same position. And having little carbons in the middle here, what it does to steel is it makes it stronger because in order to break steel, think of a force. If I've got a force moving right here, okay, because I've got these little carbons in the way, it's really, really harder to get this, this atom to hit this atom and break it, because you've got this other smaller atom that fills in these gaps that prevents, okay, this crystal from cleaving off. These little gaps being filled, and this is called an interstitial alloy, where you have smaller atoms filling in the gaps. And when you fill in the gaps, they create more stability and strength. Harder to break and move this, because to move something you have to wiggle it and kind of pull it from its crystal pattern. But if you've got these little guys in its way, it's going to offer resistance for these two atoms to move apart or get closer. So it's not about oxidation states. It's not about melting points. It's not about being polarizable in LDF forces. It's about the fact that copper atoms, okay, are smaller than the gold, and they'll fit in the spaces, and they'll make it harder for these two gold atoms to either stretch or get closer together, because they'll prevent that, and that'll give it its hardness. And that's why 42 is C, and that's an example of an interstitial alloy that's much smaller than the other atom it's being mixed with. The other one where it fits in would be substitutional, but 42 is C. Moving on to 43. All right, so number 43, we're talking about PES. We're talking about photon emission spectroscopy. And what we basically have here is we have the photoelectric effect. Very simply, we have an X-ray with very, very high energy per photon is hitting a compound, some atoms. And we have to understand that we're hitting different atoms every time. And what that does is it ejects electrons from this. Okay, so we're adding photons that have a greater binding energy, okay, and therefore these electrons have a certain speed. And as we learn from the photoelectric effect, we have the binding energy is the energy to remove the electron. And if you have a photon who overcomes this threshold and goes a little farther, this extra energy beyond the binding is kinetic energy. So we know that electrons are held by different amounts of energy. Electrons that are held closer to the nucleus, like the 1s electrons, have the highest binding energy. Okay, and electrons that are held farther away, like 1s2, 2s2, 2p5, these electrons are held farther away, and they're going to have less binding energy. So if I've got core electrons, my binding energy is going to be much higher if I remove them, which means the amount of energy right here, okay, is left is going to be small, which means electrons that come off this are going to move much slower than the electrons I pull from valence electrons that have a lower binding energy. They're going to have a much higher remaining kinetic energy, and these guys will move much faster. And what we do is basically put these electrons that are moving under a electromagnetic field to essentially bend them. And the ones that go slower, okay, are bent more than the ones that go faster. And we can measure when they hit the plate, okay, based upon voltages, or I should say amperages, how much electrons are being passed to these positions. We can measure essentially what we call the binding energy, and we can compare where the electrons are being held. The bottom line is the ones that are going faster, okay, are going to hit this plate a lot farther down. So the ones that are going slower, that hit the plate over here, that are bent more because they're going so much slower, all right, they're the ones that have the greatest binding energy, and those are the core electrons, and we basically put that into a spectrophotometer to read those distances and those speeds. Bottom line is, okay, at these positions we measure the relative blips. For instance, you look at the height of this is the same as the height of this, okay, but the distances are different for different elements. Notice oxygen, and they're telling us these are both 1s electrons, okay, which by the way are going to have a pretty high binding energy because they're close to the nucleus. So they both were slow and they got moved the most, or they got bent the farthest, and therefore they move the least, okay? But it doesn't really matter. When you look at this, who's going to have the greatest binding energy? Even if you didn't understand anything I said about photon emission spectroscopy, who's going to have greater binding energy? A 1s electron from a nitrogen atom or a 1s electron from an oxygen atom? Now, what do we know the difference? Well, nitrogen and oxygen, if you go to your periodic table, atomic number 8, atomic number 7. What does this mean? Remember, fluorine is atomic number 9. Well, in the same energy level, and this is n equals 2, as we go across, we know the atoms get smaller. Their radii get smaller because their nuclear charge increases, or we say the Z number increases, which means what? We're adding protons. And protons are now pulling in those orbitals, those electrons, a little more tighter. So the reason why oxygen has a greater binding energy for its 1s electron than nitrogen is because oxygen has one more proton. It's Coulomb's law, isn't it? Okay, having one more proton means it has a greater positive charge, and therefore it holds on to those electrons much more tightly. Therefore you need what? More energy to remove them. So it's not about being half filled. It's not about more electron-electron repulsions. It's not about electrons in the p sublevel providing more shielding. It's about, and I'm not showing this choice, so I'll rotate down. It's about the nitrogen having a smaller nuclear charge. Nuclear charge means the charge due to the protons, because in the nucleus you have protons and neutrons, and only the protons have a charge. So the nuclear charge is essentially the Z number. Okay, so the reason why, which of the following state best accounts for the peak of the upper spectrum being right of the peak? Well, if the upper spectrum up here is like nitrogen was over here to the right of the peak, it means it has a lower binding energy, which means it has what? Less protons, which means a smaller nuclear charge. Okay, 43 is D. Number 44. Number 44. All right, we've got two compounds, and we've got boiling points. Okay, so nonane and 2,3,4-trifluoropentane almost have identical molar masses. Okay, this normally means that they have a number of electrons. But nonane has a significant higher boiling point. Which of the following help explains this observation? Now, this question could be in a part 2. Why would nonane have a higher boiling point? Well, we should answer, if this was a part 2 question, that nonane has LDF forces only, and 2,3,4-trifluoropentane has LDF forces, dipolar forces. Okay, so this should have collectively more forces. Because it has two forces collectively, you would think 2,3,4-trifluoropentane would have a higher boiling point. It does not. Okay, so what's going on here? Even though that this has LDFs, and it has an additional force of what? Dipolar, meaning it's a polar molecule. And why it's a polar molecule? It has a asymmetrical distribution of charge due to these dipole moments not canceling out. This one is only LDF. So you would expect this one to have a higher, but it doesn't. So this means what? This must mean that nonane's LDF's forces are so great that it overtakes or supersedes the LDF and dipolar forces collectively. Right? Its LDF forces are so great that they're greater than both the LDF and dipolar forces put together. Okay, now that's not really what any of these choices are talking about, so we have to go there. So choice A, the CF bond is easy to break than the CH. That has nothing to do with this. When we talk about boiling points, we never talk about bonds. Never. We're talking about intermolecular forces between molecules. That means nonane is attracting itself stronger than 2,3,4-trifluoropentane is with itself. These are attractive forces. These are not bonds. Nonetheless, we're not talking about the bond energies to break this. It has nothing to do with it. So A is probably the worst choice. Sorry if you picked it. B, the CF bond is more polar than the CH bond. That is true. I mean, in fact, the CH bond we don't consider to have any polarity. And this is a true statement, so this is a good distractor for some, but it's not a true answer. It's not true for this question. Okay, careful about that. 44C, the carbon chains are longer in nonane than they are in 2,3,4. Ooh, this is what's speaking to the fact that these LDFs are so large, they're greater than the LDF of this and the dipolar force of this one. And why would these LDFs be so much stronger if they have about the same number of electrons? It's because that this one is what? What would be the key word? More polarizable. I'm answering this as if this was a part 2 question. It's more polarizable because of its shape. The longer chain makes this cloud of electrons easier to move in one direction than another. This is more circular. So because of the more polarizable shape, the elongated shape, the LDFs are greater. And that's what C is speaking to. And C is the answer. D, the carbon chains are farther apart in a sample of nonanes than they are. The carbon chains are farther apart. Okay, not sure where they're after there, but that's a distractor that some people do basically pick. But C is the answer. C is speaking to the fact that having an elongated shape makes it more polarizable and therefore increases its LDFs greater than the 2,3-trifluoropentane and therefore have a greater boiling point. Okay, so 44 was a subtle question talking about the polarizability of the shape, and 44 is C. Now I went over it as if it was a part 2 because I could see that happening. On to 45. Number 45 through 47 is a cluster question based on the galvanic cell. Luigi Galvani and Alessandro Volta both were given the I guess the credit for developing a battery. So we have voltaic cell and we have galvanic cell, all produce positive volts. Okay, so what we have here in 45, what is the standard cell? That's E0 of cell under standard conditions of the galvanic cell. It's a battery, so we expect positive volts. We don't see any negatives. And we're talking about cell Z. And Z, as we say here, half cell 2 and 3s are involved. Why? There's a half cell in a galvanic cell or a voltaic cell because one side is going to be oxidation and one side is going to be reduction. You're going to separate the side that releases electron, the side that accepts. So in half cell 3, there's iron and there's iron nitrate. So this side here, of course, is Fe, and we always have the same ion of that element, and this is Fe plus 2. And of course, we're going to have, that's your anode, because that's where oxidation is going to occur. Electrons going to be coming off. Now we're going to have the other cell being copper, and the others, and this would be the copper, and we have copper plus 2. Don't forget we're going to have some sort of a salt bridge here. That could be a U-glass tube here. But the bottom line is we got the anode is going to have electrons flowing to the cathode. Why? Electrons are going to be pushed from the anode. What happens in the anode? Oxidation. We push electrons, and something in the cathode, red cat, that's where reduction occurs, is going to pull the charge this way. Okay, any case, they want to know what's happening in cell Z, which is this reaction here. Okay, and they want to know what the net potential is. Okay, well, we know that if we knew and we had our reduction potential tables that they used to give us, we could calculate this. Okay, and we should know that iron loves to oxidize and copper plus 2 loves to reduce, and so electrons will be passed around. Now, you could come to this answer what Z would be. Okay, now we don't have any value given to us. We have to figure that out, obviously. And so what we're going to do here is use the reactions above where we have the standard cell potentials. Notice they're all positive as well. And notice we're using aluminum as both the element giving off electrons. This would be the anode for both, and it's going to force the electrons to the copper plus 2. And the copper plus 2, in this case, is going to help pull the electrons along. Now, we notice when we change the oxidizing agent, or the element that is, or the species that's undergoing reduction, that's in this case either going to be copper plus 2 or iron plus 2. When we change this system, this battery, notice the voltage drops, and that tells me that the iron plus 2 is not very good at pulling electrons. If this was okay, so that makes a lot of sense, because iron is really good at oxidizing. Terrible going one way, you're good at going the other. So it makes sense that this one is dropping the second voltage. Given the same aluminum, the voltage drops when we add an iron plus 2, because the iron plus 2 is not as strong as a oxidizing agent or oxidizer. It doesn't help pull electrons. In fact, the aluminum has to overcome the poor reducing ability of Fe, or the poor oxidizing ability of Fe plus 2, because it doesn't really do a good job at pulling electrons. So aluminum has to overcome that, and that's why it drops. And so some people can see B right away as the answer, is that difference. But what they're after, and what's really safe to do here, is look at the reactions given. They don't give you net potentials, but they give you the reactions, and they're always about manipulating their reactions in oxidation and reduction. So this is going to be the overall. And if you don't see it, look at the first reaction, aluminum plus copper, and then we're going to have aluminum plus 3. Now, I want to get rid of the aluminum, so I'm going to flip one of the others. So think about this. I want iron on this side, and iron is on the other side. So I'm going to flip the second reaction. Yeah, if you can see it, by flipping the second reaction, we should overall cancel out to this overall. And if you don't, let's just draw it quickly. So I have aluminum plus, I'm going to leave out the coefficients for speed, copper plus 2, and this goes to aluminum plus 3, and this goes to copper. Okay, in the next one, we're going to flip it, put the iron on this side. Why do I do that? Because I want the iron as the anode in the galvanic cell C. So iron plus aluminum plus 3. And then we're going to go to aluminum. And then the iron plus 2 here, 2 plus. Okay, so what we're going to do here is we're going to basically cancel out to get the overall, and the overall is iron. Now, of course, what we're going to cancel out aluminum. We don't want that there. All right, and then we want aluminum plus 3 to cancel. And so what you're left with is iron, copper plus 2, and you're left with what? Copper, and iron plus 2. Okay, and if we were to kept these coefficients, and people, if they don't see it, this was a 2 aluminum, 3. I guess I need to put that in to give you more feeling of how this works. 2, 3, 2, 3, and this iron that flipped was a 3. This aluminum was a 2. This aluminum was a 2, and this iron plus 2 was a 3. So if you look, the aluminum's canceled. So they're gone. The aluminum plus 3 canceled. They're gone. Okay, so what are you left with? A 3 to 3 to 3 to 3. And that's how you get the 1 to 1. Notice there's no coefficients there. But the bottom line is, what did I do? I took the 2.0, and then because I flipped this reaction, remember it's positive volts, which means it's spontaneous. If I reverse it to get the overall, it has to be negative 1.22. And that's where we get the 0.78 volts. Okay, and you might see that a different way, and there are a couple different ways to do that, but I like to go over this way because it seems like when there's a redox reaction involved, they want you to manipulate the equation to get the overall. This is, I think, the clearest way to see how this works. Okay, so 45 is B because of essentially manipulating these equations to get rid of okay, this oxidizer to get that oxidizer. So it's just flipping the second and them together. And when you flip the second, you're flipping the E0 of cell. Don't, okay, as these other choices are trying to distract you, multiply or divide by 3. These values are independent of the electrons' coefficients. They are basically measurements of pathway based upon the ability of the aluminum to oxidize and the other elements that are trying to reduce. So the answer 45 is B. On to 46. Okay, number 46. In number 46, in galvanic cells Y and Z, so we're talking about these two galvanic cells, okay? That's what we're talking about. Which of the following takes place in half cell 3? So they're both using half cell 3. If we're not sure what's happening, I know we have a lot of stuff going on here. In half cell 3, we've got the iron solid sitting in iron nitrate. All that means is I've got myself a half cell that's connected to the other half cell, and we have iron plus 2. Why plus 2? Because if it's hooked up with a nitrate, nitrates are always soluble, and because each nitrate's -1, there's 2 of them. We have iron plus 2, and which is, again, if you didn't have to know that, it's kind of written right there anyway. Okay, and then we're sitting in a metal of iron. That's the half cell. This is the metal iron sitting in a solution of Fe plus 2. I'll just write another one here because I can. Okay, now either it's going to what? Do 2 things. It's either going to oxidize or reduce based upon essentially how the other half cell, okay, is doing. Now let's see. So they're saying in the question, during Y and Z, which of the following takes place? Well, in Y, let's clear this stuff out here because it's getting kind of complicated. But if you look at Y, okay, the Fe plus 2 is getting reduced. So that beaker would be taking on electrons, or being forced to. The standalone metal can only lose electrons, and the Fe plus 2 is gaining them to become Fe0, standalone metals. How did I go from plus 2 to 0? Well, I must have gained 2 negatives here. So in this galvanic cell Y, the Fe plus 2 iron combination, the Fe plus 2 is getting reduced. Now, in this Z, okay, the Fe is now becoming Fe plus 2, and how does it go up in charge? Because it's giving electrons. So in Z, it's getting oxidized as it loses, right? Leo, the lion, says Gur. So loses electrons here. So here it's gaining, here it's losing. So reduction occurs in both X and Y? No. Oxidation? No. Okay. It's getting reduced in Y. There it is in C. And it's oxidizing, okay, in cell Z. In Z, you see the standalone metal becoming Fe plus 2. So that's why C is the answer, and D makes no sense because it's the opposite of what you just said, oxidizing in cell Y. Well, no. If it's oxidizing in cell Y, Fe2 plus would lose an electron, become Fe plus 3, but it's becoming Fe0, so this is getting reduced. Okay, so 46 is C. On to 47. Okay, number 47. If the half cell containing 1.0 molar iron nitrate in galvanic cells Y and Z is replaced with a half cell with what? Ooh, with something that's even a lot more concentrated than the original. So we're basically putting in a lot more, 5 times the concentration, or 500 times the concentration of the iron nitrate. Don't forget, the iron nitrate is essentially going to produce Fe plus 2. So what we're doing to this concentration is we're increasing it. And we should know when we change the concentrations, we are going to change the what? All right, the amount of spontaneity in the forward and reverse reaction, right? Absolutely. Okay. All right, so remember we have an equilibrium here, and we want to be as far away as possible because we want the farther away possible, the more spontaneous we'll be. So we want, okay, Q versus the K to be as small, this is smaller sign, less than K, so that the farther we are from the equilibrium, the more spontaneous and greater the positive voltages. So we're going to mess with the concentration. This is a Le Chatelier's problem. Okay, so let's do it. So if we increase, now they're talking about for the two galvanic cells Y and Z. So look at Y first. So if we're going to increase this, and if you need to, do the stress and the response. The stress is what we do. We're going to increase the amount of Fe plus 2. And what the response is to lower the Fe plus 2. So how does it do it? It uses it up by shifting forward, which means we're going to make the forward pathway more spontaneous. And so the voltage has to increase. Remember when we manipulated our batteries trying to make more voltage? Remember, the positive voltage represents spontaneity. How do we know? Because delta G, one of our last formulas, is equal to what? Negative N Faraday's constant E0 of cell, which is the voltage. Alright, so if I have the voltage, but, okay, and this is the amount of balanced electrons, and if that voltage is positive, okay, and the more positive it is, it's going to, with this negative number in front, make it delta G even more negative. Bottom line is more positive volts, the more spontaneous. So we're going to increase the voltage as that battery is going to go forward with a better thermodynamic pathway. So the voltage is going to increase in cell Y for sure. Now because in cell Z the iron plus 2 is on the product end, by increasing this concentration, it's going to shift and become more spontaneous in the reverse. And if it's becoming more spontaneous in the reverse, okay, that must mean that our forward is becoming less spontaneous and our voltage would have to drop. Okay, this battery's dying, has a less ability to go forward, so the voltage cannot be as high. So there's a decrease in Z. Okay, and that's why choice C is the answer. Okay, a little Chatelier's problem. Don't forget that positive volts, the greater the positive volts, the more spontaneous the forward reaction is. All right, 47 is C, on to 48. Number 48, for which acid is the value of the acid dissociation constant Ka the smallest based upon this table here of different acids? Well, notice they all have the same concentration per row. And if I have a small Ka, what's Ka? Well, Ka is an equilibrium constant, right? It's Kq. It doesn't matter if it's Ka, Kb, K. But what it is, it's the concentration of the products over the concentrations of the reactants. Coefficients become exponents, and solids and liquids do not apply. And what we know is Ka specifically is equal to the products, okay, over reactants. And we know that all Kas, if they're, I should say, get rid of that equal sign, if all Kas are all equilibrium constants, okay, if they're greater than 1, then therefore there are what? More products than reactants. And if the Ka is less than 1, or any equilibrium's less than 1, okay, then we're going to have a lot more reactants than products. So what are these products and reactants? Well, for acids, it's going to be the Ha, the undissociated acid, into its proton, which is a product, and its conjugate base, in this case A negative. And that's what goes in there. Okay, but the bottom line is they want the smallest Ka. And the smaller the Ka, the greater number of reactants. Hey, that must mean that this, okay, is in larger quantity than the products because this barely goes forward. Hey, small Kas are for weak acids who barely dissociate into their protons. They stay mostly as undissociated acids. So if they're going to produce a lowest amount of H pluses, I'm looking for the smallest acid. I'm looking for the acid with the smallest Ka. I'm looking for the weakest acid, which means it produces the least amount of H pluses. Therefore, the pH should be the greatest, right? What is pH? Negative log of the H plus ion concentration. If this was a large number, Okay, like 1 times 10 to the negative 2. The negative log of that would be 2. If it gets even bigger, like 1 times 10 to the negative 1, the pH, the positive value of that exponent, is be what? Be 1. So the pH gets smaller as the H plus ion increases. So if this barely goes forward, the amount of H plus is going to be really low. Like compared to these numbers, like 1 times 10 to the negative 3, and the pH will be higher. So the one with the largest pH per any concentration of any row is acid 1. It is the weakest acid, and it's got the Ka that must be the lowest, which shows you it has the weakest ability to dissociate into a proton in its conjugate base. 48 is A. On to 49. Okay, number 49. Which of the 4 acids listed in the table is hydrochloric acid? HCl, we should be aware of, is a strong acid. Now, if it's a strong acid, there's something we should know. That means there's complete dissociation. That means every single HA becomes H plus and the conjugate base. This is a completion reaction. There's no Ka. Ka is extremely large because we have the largest amount of products. So if every single hydrochloric acid molecule becomes an H plus and a Cl negative, we're going to have the largest amount of H pluses available per any other acid, so assuming the rest are weak, and therefore it should have the lowest pH. So if I look at my choices, okay, in my table, the one with the lowest pH looks like acid 2. All right. Not only that, look at this. The concentration of the acid is 1 and the pH is 0. Look how low that is. All right. So if I have a 1 molar concentration of an acid, okay, what's the negative log of 1? The negative log of 1 is 0. So this is showing me that the concentration matches the exact concentration of my H plus ions, right? So that must mean a strong acid there. So pH, so 49 is the, if you didn't see that or understand that, doesn't matter. The one with the strongest acid is going to produce the greatest amount of H pluses sitting in water, and therefore the one with the lowest pH for every row, each different concentration, is acid 2. So 49 is B. Okay, on to 50. Before I move on, one point I should have made here is that if you're going to use the molar concentration of the acid in this to be the strong acid, another reason why it is because there's no equilibrium. If it's a weak acid, just because we know the concentration, we would have to do a what? We would do an equilibrium problem where the Ka of the acid is equal to x squared over the initial concentration to solve for the H plus. Here we actually can do it directly. This 1 gives me 0. I know you can't do this in your head, but the negative log of 0.5 isn't these values. So anytime you have the concentration of the acid and that reflects exactly the pH by doing a negative log of it, we're saying the concentration of the acid is the concentration of the H plus, and that only works if it's a strong acid. So I meant to say that. On to number 50. Okay, number 50. Of the following species, which has the greatest concentration in a 1 molar solution of acid 1 at equilibrium? Well, as we have said and solved for in other questions, acid 1 is a weak acid. And if we don't know that, we should understand why. It has the highest pH of any of the acids for any concentration. As I explained before, having a high pH means you have the least amount of H pluses, which means you have an acid that produces the least amount of H pluses, means it barely dissociates, which means most of your beaker sitting with a weak acid has the acid undissociated, meaning it's with its proton, HA. A lot more of this is existing, and a little bit of it is H plus with its conjugate base. That has to be clear that this is the weakest acid, which means only a small percentage of it ionizes. Okay, that's important as we go through the question or the choices here. Okay, so which of the following species has the greatest concentration in a 1 molar solution of the weak acid that barely dissociates? Okay, because it's acid 1 they're talking about. Well, first of all, we can't pick A because A is the hydroxide. And even though it's a weak acid, the pH is still way below 7. Anytime the pH is what? Less than 7, we should know that there's more what? There's more H3O plus or H plus than what? There's greater, what's this double sign here? If it's less than 7, there's a great amount of H as compared to hydroxide. Yeah, so there's more of this acid component of water than base. So that obviously it's acidic, so you should have more H pluses or H3O pluses, so this can't be the answer. So this might be an answer because we know that this is greater than the hydroxide if the pH is, I should write that, pH is less than 7, acidic range. So that's got an opportunity. And so what is the concentration of H3O plus? Now if we go to 1.0 molar, okay, it's 2.44. Let's round to 3. Let's make that 3. Okay, so if we make the pH round to 3, so what's a big 3? Or we can round to 1. Let's make it 3. Who cares? All right, so the pH is 3, and that's equal to what? 3 times 10. I'm sorry, that's equal to 1 times 10. I can do this. 1 times 10 to the negative 3. I guess I can't. So 1 times 10 to the negative 3. That's the concentration of my H plus. Okay, or H3O plus, it doesn't matter. Okay, but compare that to the concentration of the what? The acid. The acid's 1 molar. Okay, whatever the acid is, HA, that's equal to 1 molar. Now, some of it dissociates, but since very little does, it's going to be still close to being 1 molar, and that's a lot bigger than the H3O plus. And the key to this question is a weak acid's barely going to dissociate, and it's always going to be a much greater concentration than anything else. Okay, so C is the best answer. Now the conjugate base of acid 1 makes no sense because this barely goes forward, right? HA barely moves to H plus and its conjugate base. Having a tough time here with this thing. And so therefore, since it barely moves forward, you're going to barely make any conjugate base. So it's a weak acid. It barely dissociates, but it's still going to, what? Be in larger amount of quantity than the H3O plus and definitely the hydroxide and definitely the conjugate base. 50 clearly is C. The undissociated acid at 1 molar is in greater concentration than the rest of these species because it is a weak acid. Number 51. So 51. If equal volumes of 4 acids at the concentration of 0.5 are each titrated with a strong base, that means they're going to be driven if they're a weak acid, which will require the greatest volume to reach the equivalence point. Now we all know the equivalence point, at least we should, for measuring pH over a volume of base added. We're going to get something like this. The equivalence point is going to be the volume needed when the what? When the moles of the hydroxide added equal the moles of the protons that the acid have, and that's important. Now this would be, okay, the volume here. This value, I should not draw that, okay? It should be where my dotted line is, yeah. So clearly this volume is what we're after. How much volume of a base? Now the base is all going to be, okay, the same strength, okay? And we're going to say that all the acids are at the same strength. Okay, so the biggest distractor, and most people jump at, well, acid A is the weak acid. It has the highest pH of all the acids, so you're going to need what? A lot less of it, but you missed the point of all of our titrations. If this was a strong acid, or a weaker acid, we'd start up higher, right? But then we would have a smaller asymptote. If I had a stronger acid, we'd start a little lower, but we keep having that asymptote at what? at the same volume. If all these acids have the same concentration of 0.50 molar, because this reaction is for the strong acid or weak acid, mostly for the weak acid, the strong base is going to make the weak acid act like a strong acid. It's going to pull every single H off. Don't forget, titrations are driven reactions, so it's independent whether they're what? Weak or strong. Okay? Even if they're weak and not good at dissociating, like acid 1, a strong base will force its hand stoichiometrically. So as long as the weak acid and the stronger acids have the same concentration, okay, you will need exactly the same volume, because the strong base will titrate them to at the same equivalence point in terms of volume. Now the pH at equivalence point will be different based upon the strength of the acid and base, but the volume be the same, because that volume of base represents a stoichiometric finite value of hydroxide needed to match the H in the acid, and that's independent of how well they give them off. It's whether or not they have them originally, and they're all the same concentration originally. So the answer is D. All the acids require the same volume to reach the equivalence point. The pHs will be different, but the volume will be the same, because they all are the same concentration, and how well they give off the H plus is independent here. It doesn't matter. If it was sitting in water in 0.1 we talk about, it would matter, but here we're driving it forward stoichiometrically. For every OH minus, it pulls an H, whether the H comes off easily or not. So 51 is D. Really great question there. 52. Okay, number 52, 25 milliliters sample of a 1.0 molar solution of acid 1, which we know is a weak acid. It's a weak acid because it has the highest pH of all the other acids at the different concentrations. We talked about that in different problems above. Which of the following best explains what happens to the pH of the mixture when a few drops of the acid are added? That's after we've mixed it and titrated with 25 milliliters of a 0.5 molar NaOH. Now notice something. The sample that we have is a 25 milliliter sample. Okay, oops, right here somewhere. Okay, so the sample that we have is a 25 milliliter sample at 1.0 molar solution. Okay, and then we're going to add 25 milliliters of a 0.5 molar solution. So we'll do the math in your head. 25 times 1, okay, is 25, right? Now, do 25 times 0.25 if you want, and it's going to be 12, okay, 0.5, right? And so if you're solving for moles, and I know this has to be in liters to do that, you can clearly see that there's half as much moles of NaOH. What we're doing here is creating a buffer. And that buffer is made by doing what? Driving the titration halfway. That's right, we have a weak acid HA, and we're driving it to its H plus and its A negative. But because we're using half as much of the strong base necessary to drive it forward, what we're doing is producing conjugate base that has the same quantity as the conjugate acid. So if we want to plot this, just to get a visual of what we're talking about, remember this is pH changes, and this is, in this case, the volume of the base added. Alright, and it looks something like this. And this equivalence volume, based on this information, 25 milliliter sample of the acid, and you added 25 milliliters of 0.5 molar, okay, it seems to me that you would need twice as much of that. So you would need 50. So this should be about 50. And if you didn't see that, that's okay. So this value down here is about 50. And since we titrated halfway, we're about 25 milliliters, which is about what they're saying. So that makes some sense here. And what did we produce? Well, we produced as much conjugate base as HA remaining. Okay, if you understand that. If we had 1 molar, now we didn't, Okay, and we had 0. If we added just enough, put hydroxide here. If we added half as much, 0.5, well, what's going to happen is the limiting reagent in moles is this one, so it's minus 0.5. This is minus 0.5, and this is plus 0.5, right? And so at the end of this is going to go to 0. It's the what? Limiting reagent, and 1 minus 0.5 is 0.5, and 0.5 plus 0 is 0.5. And so you produced equal amounts, or at least you have equal amounts of HA remaining, and you have equal amounts of conjugate base remaining, and the pH equals the pKa at this point. But the point here is you created a buffer. By driving the weak acid forward lower than the equivalence point, you created a buffer region right here. And this buffer is going to prevent pH swings. So which of the following best explains what happens when you add acid? How do I know? H in front. So we're adding H+. Well, the pH isn't going to change much. That's what a buffer does. It prevents pH swings. Now, who's going to react with this extra H+? Because if something doesn't, it's going to drop your pH significantly. Well, it's going to be the base. And what's the base? The conjugate base. So the pH of the mixture stays about the same. That's what buffers do. You had to realize you're making a buffer. Okay? Because in this case, it's the conjugate base of acid 1 that reacts with the H3O plus that's produced when the strong acid is added. That's the whole point of driving it halfway, is to essentially create a larger amount of conjugate base that can react with acid as part of the buffer. So 52 is C. On to 53. So number 53, a proposed mechanism. These are multiple steps of an overall process. These are elementary steps for the destruction of ozone gas in the stratosphere. Now, you may not know what ozone is, but it's O3. If you didn't know it, you could see that in these reactions by canceling. Look what cancels. Cl cancels. Okay, this cancels. And you're left with O3 plus O gives you O2. So you're destroying the O3, okay, into O2 by having an extra oxygen here. Okay, so that's what's happening. So which of the following is evidence that the mechanism is occurring? Okay, well, realize this. This guy right here starts the mechanism because it creates this intermediate and it gets reproduced here. So you should realize if you're starting this whole chain of events by creating the intermediate that links one step to the other, remember this is the intermediate, and it's highly reactive, okay, which means this second step is probably the fast step. And this is the slow step. How do I know? Well, we have to wait for these guys to make the intermediate. Intermediate quickly reacts. Okay, so usually it's how it works, but the bottom line in this question is that what starts and creates this intermediate and thus that creates this set, or this, I would say, pathway, what creates the pathway is the catalyst. And a catalyst can be identified as something that is in the reactant side of one and then the product side. Catalysts never get consumed, they get produced. So the presence of the chlorine, which is the catalyst, increases the rate of the overall reaction. That's what catalysts do. And why does it do that? Well, if you had a potential energy diagram, and I don't know if this is exothermic or endothermic, but let's just assume it's exothermic. If you've got a catalyst, it's going to create these two-step processes, or this two-step elementary steps that collectively have lower activation energy than the activation energy without the catalyst. And what that means is the E of A has been lowered overall because of this pathway that chlorine created. And therefore, with the same energy available, there's going to be more effective collisions that create this this reaction. The activation barrier that prevents the reaction from occurring has been dropped, and for the same amount of energy present, you're going to have a lot more collisions, right? If you want to look at it a different way, here is an overall distribution, Boltzmann distribution of speed of certain molecules at a certain temperature. This represents the E of A. The only few amount of the molecules have enough energy to overcome that barrier. But if you were to lower E of A, move it downward this way because of a catalyst, now you have what? All of these remaining molecules, okay, that have now the energy to collide, to make collisions effectively. And that's why the rate of reaction increases. It changes the pathway by lowering the activation energy, because the collective activation energies of this mechanism, this pathway, is lower than without. Okay, so 53 is A. On to 54. Number 54. Based on the data in the tables, which of the following statement provides the best prediction of the boiling point of NaCl? Well, we have NaF and MgO. These are ionic solids, which means they're positive ions attracting to negative ions in some kind of crystal arrangement. Oh, this should be smaller. Okay. More or less. Now, the boiling points are very high with ionic compounds because positive and negatives attract each other very strongly, and in these crystal arrangements, they're very stable. Now, these attractive forces between ions, or electrostatic forces, is based on Coulomb's law. And Coulomb's law is equal to some constant times the size of the positive charge times the size of the negative charge, right? Divided by the distance between them, close to the distance, okay? So if you look at that, okay, and you say, well, where does the boiling point of NaCl fall? Well, NaCl says sodium, so it's about the chlorine, so we compare fluorine to chlorine. Now, fluorine is a smaller ion. Of course it is, because it's an N=2 element. It's in the second row. The N number indexes size. This is N=3. It's bigger ion because it's in the third row. So being smaller means what? That means the distance between these ions in the crystal is going to be smaller for fluorine. Therefore, if the denominator gets smaller, then the force of attraction, this is F, the Coulombic force, is greater, and therefore it'll be harder to pull these apart. So I'd expect NaCl with a much bigger ion, okay, much bigger ion here. The size of the charge stays the same, but I expect it to have a greater distance, right? Let me try that. So it's greater distance. The denominator is getting bigger, which means the force of attraction is getting less. So NaCl will have a lower boiling point than NaF, because the Coulombic attractions, Coulomb's law, are weaker than NaCl. And that'd be because the Cl is a much larger ion and has a greater distance to the positive ion. And of course, this works by charge density. If you're taking a negative and making it a bigger ion, this positive is going to feel that ion much less, as that -1 is spread out over a greater area. That's what Coulomb's law is, charge density. Any case, charges are the same, but of course the distance is the factor here. Okay, looking at, so 54 is A, but look through the choices because it is fun. Sodium chloride will have a boiling point between NaF and MgO. Well, no, it's going to be less because fluoride's a smaller ion. MgO, my gosh, look at the size of the charges. Now you're going to increase the size of the charges, and it's smaller. So if the top numbers get bigger and the denominator gets smaller, boy, that's really going to compound your your force of attraction to be really large. Okay, so that's not going to work there. NaCl have a higher boiling point than MgO? No. MgO has a smaller denominator. The D is smaller and it has higher charges. It's going to make the force of attraction of coulombically be huge for the same reasoning. So that doesn't make any sense. And NaCl have a higher boiling point than MgO. Still, for the same reasoning, I can't even continue. It can't. Okay, and they're talking about transfer electrons. They're talking about a chemical reaction. Boiling is a phase change from a liquid to a gas, and phase changes are not chemical. This is talking about a chemical reaction. Okay, so A is clearly the correct choice. A really good review of Coulomb's law. 54 is A. On to 55. Number 55. The table above shows that the values of Ka for 4 weak acids. which of the following pairs of chemical species, when combined in equimolar amounts, results in a buffer with a pH closest to 7.5? Well, a buffer, we should know, is going to be a conjugate acid with its conjugate base. It has to be conjugate because, as we've learned, conjugate base pairs, conjugate means the what? Same chemical plus or minus an H. And we learned that the Ka of that conjugate acid times the Kb of the conjugate base of the same chemical is equal to Kw. So if I've got a stronger weaker acid, that means I'm going to have a weaker conjugate base. So stronger the conjugate acid, weaker the conjugate base. We know that makes sense. Strong acids, okay, do not go in reverse because they have the what? Weakest conjugate bases. They can't go backwards. But if I've got a weak acid, that means the conjugate base has a great ability to reform the acid. So because conjugate acids are inversely related in their abilities, they can't react with each other. Okay? Therefore, you're going to have an acid and a base who can't react with each other. They're to accept an acid or a base in a buffer. Okay, so the first thing I do is find conjugate pairs. So if I look at A and B, these are not conjugate. These are not plus or minus 1H. B is. Look at that. There's an H, there's a conjugate acid, there's a conjugate base. Look at C. There's the H, there's a conjugate acid, and there's without the H. Okay, and this is also a good example of a conjugate acid-base pair. So we get rid of A. But how do I find the pH closest in equal molar amounts of conjugate acid base? Oh, well, wait a minute. We know this. In equimolar amounts, what are we going to have? We're going to have the half equivalence point, the max buffering region. And what do we know there? If we have equal amounts of acid and base, we know the pH equals the pKa. Okay? Because the log of the conjugate, what? Base over the conjugate acid is equal to each other, and that becomes 1. The log of 1 becomes 0. So let's take our Ka, which is given to us, and we can just estimate what the pK would be by doing a negative log. And since they want 7.5, and these acids are pretty far apart and we don't have calculators, it's easy to do. Like I could make this 1 times 0 times the negative 4, and negative log of this would be a pKa of, if I just assume this is 1, would be equal to 4. It's the positive value of the negative exponent. If this becomes 1, this becomes a pKa of 5. This one I know is a 3, but make it 1, it's a pKa equal to 8. This is a pKa, again, rounding this to 1, 1.0, equal to 10. Which one is closest to 7.5? There it is. And I would need this acid, weak acid, conjugate acid, with its conjugate base, because it doesn't react with each other. And of course that is choice C. 55 is C. On to 56. Okay, number 56, we've got a particulate diagram, and we're going to add silver nitrate to magnesium chloride, and we're going to precipitate. They're telling us it's happening. Obviously, the silver ions are going to combine with the chloride ions and make that precipitate. Okay, and then we're going to have our spectators. All right, so they're saying, after all that's being said, which of the following solutions could be represented by the diagram below? Now, X and Y are 1 liter. And you can notice here that, okay, this must be twice, it's 2 liters. They're saying, okay, given all that, assuming the volumes are additive, which of the following sets of solutions could be represented by the diagrams above? Now we have some molarities here. And I'm comparing molarities of one beaker to the other, so really oftentimes it's good to count. So let's count the amount of silvers. 1, 2, 3, they're plus 1, 4, 5, 6, 7, 8, 9, 10. All right, so I've got 10 silver ions. Okay, let's count the magnesium, which is +2. We should figure that out because chlorine's -1. And there's our +2. 1, 2, 3, 4, 5. So when I compare the concentration of silver nitrate to magnesium chloride, now there's 1 magnesium per one of these magnesium chlorides. So I'm going to use the magnesium as the indicator of the concentration. There is half as much magnesium as there is silver here in the same 1 liter volumes. So I have to look at my beakers and see which one is half. So 2 to 1 between beaker X, which is here with the silver ions, and Y is here with the magnesium. So the 2 to 1 is great. So it's either C or D, and that's all I had to do there. Now, when I go to beaker Z, I notice I have 1, 2, 3, 4, and 5. So it would be really easy to think, well, I have the same number of ions here, so the concentration of the magnesium nitrates based upon how many magnesiums I have, because there's 1 magnesium per one of these formulas. And since I have 5 magnesiums here and 5 here, you may think that I have the same concentration in beaker Y as beaker Z, and it's easy to see why you might pick C. But, little catchy little question, this container is twice as big. And what happens when you pour 2 solutions together? Don't we use the dilution formula to figure out our new concentrations? Remember we did that with KSPs? So it was 1, but by diluting this to having twice the volume, the concentration of the magnesium is going to be half, and that's why D is the answer. Understand totally, if you're going fast without time, why you would pick C. But again, 2 to 1, twice as many silvers to magnesiums, and then again, the magnesiums are the same here, but the volume is twice as much. You're adding 2 solutions together, and so that solution gets diluted, double the volume. Remember, molarity is what? Moles over liter. The moles stay constant, but the liter got doubled. So you're going to have the molarity there, and that's why 56 is D. Onto 57. A sample of N2O5 was placed in an evacuated container and the reaction represented above occurred. The value of the partial pressure of N2O5 was measured during the reaction and recorded below. Time increased, amount of the reactant decreased. We have ln of the partial pressure, and then we also have 1 over that. Notice we're not using concentration, we're using partial pressure, so we have the what? We have the parentheses. So, which correctly describes a reaction? They want to know if it's first order, 0 order, second order. Well, guess what? The first thing I do is see if I can find a half-life. Okay, and that's 1/2. Well, let's see, 0 to 100 is 75. Okay, and let's see here. So, I don't know if I can't. What I see here is I see that the half-life, 150 goes to 175. Whoa, that's half, right? 75 plus 75 is 150. And so the half-life looks to be like 100 minutes. Now, if it's first order, that 100 minutes should stay constant. What's half of 75? That's what, 37, 0.5, which is 38. So, hey, it halved again, and the time between this point and this point is still 100 minutes. And what's half of 38? 19, and that's still 100 minutes. So I can see that the half-life stayed constant, and therefore the decomposition of N2O5 is first order B. Okay, now I could have also seen that the ln of this, remember in our reference tables we know the first integrated rate law formula. Okay, the ln of our, in this case, be parentheses, but we'll do it ln of A of some time period minus the ln of A of some initial concentration equals negative KT. Okay, and of course you can put this positive over here as your y-intercept, and you got y equals mx plus that positive value, which is B. And if it's a straight line, then these values should be very similar. 5.0 minus 4.3 is what? 7. 4.3 minus 3.6, 0.7. These all are consistent, so you get a straight line here, and obviously you're going down from 0 to 300, which is what you expect if you do the ln of your concentration. So that's why there's another way to consider that to be first order. In any case, 57 is going to be B. Onto 58. Number 58. Based on the periodic trends in the data table above, which of the following are the most probable values of the atomic radius and the first ionization energy of potassium, respectively? All right, well, potassium and calcium are N equals 4. You're in the fourth row, quantum number 4. And of course, calcium is an alkali metal, and potassium is an alkali metal, and then calcium is an alkaline earth metal. And so this is row 1, column 1, column 2. So they're in the same row, same energy level. And what do we know going across? Calcium has one more proton, which means its nuclear charge is a bit greater. And so the atomic radius of calcium should be a bit smaller. As we go across the periodic table, the nuclear charge, or the Z number, the number of protons, increases. And as that happens, we pull on those electrons coulombically to be closer. So we pull electrons in orbitals, and so the atomic radius gets smaller. So we'd expect atomic radius of potassium, which has one less proton, to be bigger. So 194, so I would expect the 242. Now, first ionization energy is the energy to remove the first electron. Since potassium has one less proton in the same energy level, in the same distance, essentially, because N equals 4 quantifies or indexes size, so electrons are about the same distance, the same size orbitals, but being that potassium has one less proton, its orbitals are kind of bigger in that energy level. I should say really N equals 4, they have the same number of electron internal shells of electrons, but the distance is different because of the different number of protons. Okay, so I'd expect the first ionization energy of a bigger atom to be less. Okay, these electrons are farther away from the nucleus than the calcium, so therefore it's easier to remove that electron, and therefore I expect a lower value for ionization energy because its radius is bigger, and that's why 58 is B. Not going over the choices that make no sense. And anytime we go across, the radius and this gets smaller. That's why we eventually come up to nonmetals who are so good at what? Absorbing and taking electrons, and these to the left are gaining them. So it's in a trend you should know. Atomic radii decreases going across, and also the ionization energy also increases as you go across because of that, and the opposite as you go across the other way. And it's all due to, if you're in the same row, very important, it's all due to the nuclear charge, which is tied to the number of protons. And another way to say the number of protons is your Z number. Okay, so 58 is B. Onto 59. The figure above shows that in solid hydrogen and fluoride there are two different distances between H atoms and fluoride atoms. Which of the following best accounts for these two different distances? Well, this is a molecule, and this is the same molecule, and this is the same molecule. And you should know that a straight line represents a covalent bond, which is really a pair of electrons. Dashes represent intermolecular forces, which are always going to be much, much weaker. Dashes show how the positive end of an HF attracts a negative end. Of course, that's H bonding. So the intermolecular forces are weaker, therefore the distances are greater. Stronger the bond energy, we learn what? Shorter the bond length. Of course, intermolecular forces are not ever going to be as strong as a bond. Their lengths are going to be longer. So it's the difference in strength between the covalent bonds and the intermolecular attraction, choice B. And it's important to understand this because when we talk about boiling points or melting points, all we're doing is separating the molecules from each other. We're never going to break bonds, and people will say that when we talk about a boiling point, which is a phase change. It's a what? HF, in this case, let's make it liquid, going to HF gas. Notice the chemical formula did not change, so it's a what? Physical change, but more importantly, it's not chemical because we're not breaking any bonds. We're just breaking the what? Intermolecular forces of attraction. So many people want to say that bonds are broken when we separate molecules from themselves. No, 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 no. So number 59 is B. On to number 60. Let's go for it. Number 60, okay? This chemical decomposes according to the equation above. When pure CoCl2 is injected into a previously evacuated flask. Remember, how many times have you heard that setup? Okay, so it's empty with no pressure at a certain temperature. The pressure in the flask is initially at 1 atmosphere. Okay, so after the reaction reaches equilibrium at 690, okay, so they're saying, I guess, when the flask, once you add this gas in, once you add it to where there was no pressure or nothing in an empty flask, it originally, before it reacted, was 1 atmosphere. That's important. Okay, after the reaction reaches equilibrium at 690, the total pressure in the flask is 1.2. So the pressure increased. What's the value of the Kp for the reaction at 690? Okay, so what do we mean by that? Okay, well, Kp is just like any other equilibrium constant. So Kp is going to be equal to the products. Now, these are all gases, so I'll use parentheses, CO to the Cl2 over the CoCl2 reactant. Products of reactants coefficients become exponents. Okay, so now it reaches equilibrium, and it's going to 1.2. Okay, so we have to understand why there is an increase. Okay, and that increase occurs because it goes forward a little bit. So if we use our x's, okay, if we use our x's, let's do this. Okay, so our x's, all right, we notice, and let's just kind of write this nice and neat down here to make some sense of it. So here's our reaction, and if we do a little kind of condensed ice table to see what's happening here, we know we're starting initially with 1.0, and then this is 0 and 0, and the change that's going to occur here is we're going to lose something, right? It's going to go forward because it's going to make some products, and this is going to be plus x, and what we're going to get at the equilibrium is 1 minus x, and this will be x and x. Okay, all right, great, but what's x? Well, they said that the reaction flask is 1.2 atmospheres. So one way to solve for this is the way that I would do it is take 1 minus x, okay, and then, because we're talking about the total pressure, so this is 1 minus x plus x is 2x, is going to equal the total pressure in the flask, which is 1.2. All right, and then let's solve for this. Well, minus x and 2x just give me x, and what I have is 1 minus x equals 1.2. I think we can solve for this. So that's going to be, 1 plus x, because it's a negative x and plus it's 2x. So that's negative x and 2x gives me 1x. So plus x. Okay, and I'm going to take this negative 1, so x equals negative 1 to 1.2 is 0.2. So that's pretty easy to solve, that x is equal to 0.2. Okay, now plug that in. If this is 1 minus 0.2, okay, right, 0.2, that's going to be 0.8, and this is going to be 0.2 and 0.2. So all I got to do now to solve for Kp is just plug these into these values. This is 0.2 times 0.2, or 0.2 squared, and this over 0.8. Okay, well, 0.2 squared is what? 0.04 over 0.8. You say, I can't do this. Well, isn't 0.4 over 0.8 0.5? Right, 0.4 over 0.4 over 0.8 is half 0.5. Well, 0.04 over 0.8 would be 0.05, right? That's all you got to do here. So you should get 0.05, which is choice B. Okay, and that's why B is the answer. So you had to think about this. I've seen these questions before, okay, but you had to see how much it went forward, and I used an equilibrium ice table to see what these values were, and then I used this very simple um, algebra to solve for the total pressure in the flask was 1.2. It had to equal the 2 x's we made plus the 1 minus x, and we solved for x easily to be 0.2, plug them back into our equilibrium expression, did our easy math because we didn't have a calculator, and we got our answer. Okay, so 60 is B. This concludes this part of the multiple choice part of the test. Hope this helped.